So welcome back to the next webinar in my series on modern Java by example. What we're going to do today is we're going to start exploring some of the issues related to backpressure in reactive streams frameworks, such as Project Reactor and RxJava. In order to do this, we're first going to briefly revisit an example we talked about recently that used the Java streams and parallel streams framework in order to be able to determine whether a large number of random integers were prime. And I'm going to quickly look at that, show how it's handled in terms of Java streams, and then we're going to compare and contrast that with the way that this type of approach is handled in reactive streams frameworks, such as RxJava and Project Reactor. So without any further ado, let us switch to screen sharing mode. And you can see that the source code we're going to look at today comes from two places. The first thing we're going to look at very quickly is the example we talked about the other day. This is the EX9 example in my RxJava folder. And we'll just spend a few seconds on that because that's not really the focus of the material this morning. Instead, we're going to be focusing on the Reactor, and it's going to be the EX3 example. So Reactor EX3 is where all the cool stuff's going to reside. So let's now go ahead and switch over to my IntelliJ IDE. And just here's a real quick recap of the example that we talked about a couple days ago that showcased the use of memoization in order to be able to compute, cache, and retrieve large prime numbers. And particularly the point I want to show you here is the part down here where we do the run test. So if you recall, the way this program works is we have a publisher, and as you can see, the publisher is going to generate a stream of random integers, either in parallel or not. We can control that through an option. And then it's going to go ahead and print some diagnostics we'll talk about it in a second. We then go ahead and check to see if the random numbers that are coming through as a stream are prime or not. And then at the end, we go ahead and handle the results and print the output. This is very similar to what we looked at before. The main difference now is I have this new thing called pending item count. And pending item count is going to be essentially incremented as we're coming through from the publisher. And then every time we actually subscribe and handle it, we're going to go ahead and decrement the count. Subscribe here, of course, is a loose term because this, of course, is Java stream. So every time we have a terminal operation that completes the stream, we're going to go ahead and decrement the count. And the basic point of this is to see how many requests are in the air at any given point in time. So let's just go ahead and run this example very quickly. And you'll see we're going to run this with debugging turned on. And initially, we're going to run it with parallelism turned off. So there's just going to be one thread of control. So let's go ahead and run that example. And you'll see basically what happens here. You'll notice every time the publisher publishes an event or an item, a number, we increment by 1. And every time the consumer consumes it, we decrement by 1. And because of the synchronous nature of streams, especially sequential streams, it's very synchronous, you can see that we never have any more than one pending item at a time. So let's now go ahead and turn on parallelism. So we change -p to true from false. And now we're going to run it. And you're going to see that the pending item count is going to go up, but it's never going to go any more than the number of threads that are running in parallel. So let's go ahead and run that real quick, and you'll see what I mean. So keep in mind that this particular program is being run on my quad-core hyper-threaded MacBook, which has essentially a total of 8 logical cores. And you can see that the pending item count here basically gets up to about 6 before it starts going back down. And that doesn't mean things are queued up. It just means that we have a bunch of threads that are incrementing this atomic integer in parallel, and it gets to about 6 or so before the consumers and other threads start decrementing it. So the point of this is that because Java sequential and parallel streams are fundamentally synchronous, we never have to worry about the pending item count growing without bound. So that's the key point to take away from. All right, now let's switch over and start talking about reactive stream API issues. So another, just to recap on the point we made, there's no need for backpressure with the Java streams framework because it's not really queuing the items up in a way that will keep growing and growing and growing. So when we come over and we look at the reactive streams models, I'm using Project Reactor here, but the same point applies if we were to be using the RX Java, because the features work more or less exactly the same way. Now we're going to have to consider the issue of back pressure. So let me kind of walk through this example and you'll get a feeling for why that is. So here's the example. This particular example is similar to the streams version we just looked at, though not identical, because of course it's using using Project Reactor features. It is surprising how many things are identical, and you'll see that when we go through a little bit later. So this particular program applies these Project Reactor features to implement a hybrid push-pull back pressure model between a publisher and a subscriber that are running in different threads with different schedulers. And we're also going to use it to show some other cool things here in a minute as well. But let me go ahead and just run this program. It takes a little while to run, so I'm going to run it first, and I'll kind of talk about what we're going to see here in a second. So what we're doing in this particular program is, unlike the previous approach where we basically demonstrated the use of concurrent hash map versus the stamp lock hash map versus a synchronized map, I think it was pretty clear that for the most part, concurrent hash map is the way to go. So this program just uses concurrent hash map. What we do, however, here from a benchmarking point of view is we time the benefits of using memoization versus not using memoization. So if you recall, memoization is this technique where we use the hash map, the concurrent hash map in this case, to cache the values. And if you go and have a duplicate that comes along, then we can go ahead and basically reuse the value in the map rather than having to recompute the primality check anew for every event, every sample that comes through here. So just at a high level, and then we'll dive into the back pressure stuff. We had 100 random integers. They were very large, basically up to max integer. And we use a memoizer for one of the tests, and we use a non-memoizer for the other one. You'll see how that works. So it turns out for the memoizer version, about 1/3 of the items were duplicates. So we get a big win from using a memoizer in that case. And in fact, the more duplicates in the input, the better off we're going to do by using a memoizer. Likewise, you can see for the test that didn't use the memoizer, we had to do every single prime check, even though there were duplicates, because the data in both cases was the same. And you can see, perhaps not surprisingly, that the memoizer version executes quite a bit faster than the non-memoizer version. So for the simple fact largely of all the duplicates that are involved here, if there were no duplicates, the memoizer version would actually be likely to be slower, because it's got a little bit more work to do if it has to compute the values each time, because there's some extra stuff it does with the concurrent hash map. So first thing to note, memoization is a win, especially with a lot of duplicates. All right, so just keep that in the back of your mind. Now what we're going to do is we're going to start having fun playing around with this stuff and demonstrating why back pressure is important. So let me go back over to the configuration stuff here, and you can see I've got debugging turned off, parallel processing set to true. We'll talk about what that means in a second. I have the back pressure also turned off. We'll see what that does. And we have logging turned off. So first, let's go ahead and turn logging on. And this is a really cool feature that you can get with Project Reactor and RX Java. You can actually log the events. So when we rerun this test with logging turned on, and let me also go ahead and reduce the total number of elements here to, let's say, 20, so it won't take quite so long to run. When we turn logging on, what you're going to see is something interesting. You're going to see here we had 20 elements that were generated, and this basically shows you what's going on under the hood with respect to the framework, with respect to the Project Reactor framework. So you can see here that we subscribe, and we have initially an unbounded set of requests, which means no back pressure, just let her rip. And then we go ahead and you can see we generate basically 20 random numbers, large random numbers in this case. And when we're all done, the on-complete element is emitted. And notice that all these things are taking place in the publisher thread. So the publisher is running in the background doing all these admissions. Just for kicks, and I'll come back and look at this in more detail later, let's turn on Backpressure. So that before we didn't have Backpressure enabled. Now we turn Backpressure on. Now let's go ahead and run this, and you'll see a different behavior. It would probably be even better if I tweaked a few things in terms of what the size of the request was. But even with this simple example, you can see how it works. So you can see that we end up now with 2 chunks. The first chunk, maybe actually 3 chunks. The first chunk asks for 10 elements to be emitted. And after those elements are processed by the subscriber, you can see the subscriber thread comes along and says, I'd like another 8, please. So 8 more sent. And then after the subscriber's gotten all those, then it says, I'd like some more, please. In this case, we only have a few more left, so only a few things are emitted. So this is our first taste of Backpressure. Rather than sending everything in one fell swoop, which is what we've done before, now we're chunking things up into batch sizes, or what we'll call request sizes. And you'll see how this is used to implement something called hybrid push-pull backpressure. There's many other forms of backpressure which we'll cover in other webinars on reactive streams, but right now I want to focus on the the push-pull hybrid model. Okay, so just keep that in mind as we start talking about what we're doing, and you'll see lots and lots more cool stuff as we go on here. So let's go and look at the code now. So this is EX3. We have a bunch of atomic integers that we use to keep track of the counts. We keep track of the number of prime checks. We keep track of the number of items that are pending between the publisher and the subscriber. And you'll see that this is very important to see how without Backpressure, you can have the queues that are used internally by the reactive streams frameworks grow and grow and grow without bound, which eventually will run out of memory on the computer if you're not careful. We have a list of randomly generated integers. We'll take a look at that in a second. We keep a pair of subscribers. One is the subscriber. I'm sorry, we have a pair of schedulers, one of which is going to be used for the thread that's generating, publishing the numbers, and the other is for the thread in the schedule that's subscribing to them and processing them. We have this thing called the hybrid backpressure subscriber. We'll look at that. That's really cool. We have something called a disposable composite, which we use to basically dispose everything in one fell swoop. And then here's the main program. We go ahead and create our EX3 object and run it. Here's the constructor. We initialize the prime check counter to 0 and the pending item counter to 0. We parse the command line arguments, which can set all these cool flags to make testing easy. And then we go ahead and grab how many integers we want and the maximum value for each of these integers. And then we go ahead and basically generate a stream of random integers within that range, attempting to generate some duplicates, box them all up from ints to integers, and stick them into this list. And you'll see how the list is used when we get to the publisher in just a minute. Next thing we're going to do is we're going to set up our schedulers. There's lots of different ways to do this. I have done a simple approach now. As we get further into these types of examples in later webinars, we'll do more sophisticated stuff with the schedulers. So what I do is what I do is I go ahead and make a new scheduler with one thread, a new parallel scheduler with one thread in it, and I call that scheduler subscriber, very profound name, and that's going to be the thing that's going to be used to basically consume the data. And then if we're running in parallel, if the command line flag said we're running in parallel, then I go ahead and make myself another parallel scheduler with one thread in it, and I call that publisher. If we're not running in parallel, then the publisher scheduler and the subscriber scheduler are one and the same. So in other words, everything's running in a single thread, both publisher and subscriber. And you'll see how that matters as well. Next thing I do is I go ahead and implement a hybrid backpressure subscriber. We'll look at that in a second. That implements this hybrid push-pull backpressure model. And I pass in the pending item count because it's going to need it internally to do the diagnostics. And then the last thing I do is I take my subscriber scheduler, my publisher scheduler, and my subscriber, and I go ahead and put them into a disposables composite so I can get rid of them in one fell swoop. And you'll see how that works later. Okay, so that's basically just kind of setting the wheels in motion. Here then is the run method. This is what's actually called to do the testing. I make myself a concurrent hash map because we've already decided that concurrent hash map is the way to go. And then I make myself 2 test runs. One is going to use a memoizer, which will use the concurrent hash map as a cache and only call is prime if we don't already have the knowledge of whether a prime candidate is prime. So that's how we're going to memoize it, cache it. And the other is where we just pass in the is prime method directly. And for that example, of course, there will be no memoization, there will be no caching. We're going to call is prime every single time. And as you saw, under the right circumstances, memoization is a big win, especially if there's lots of duplicates. After we run the tests, we dispose of all the disposables, we print the timing results, and then we're going to demonstrate slicing, this time using the Project Reactor features as opposed to the Java Streams features. And it turns out there's equivalent RX Java features for all the things that Java Streams can do with respect to slicing. There's a take while operation on a flux, which is very much or identical to the take while operation on a stream. And there's a skip while operation on a flux, which is essentially equivalent to the drop while operation on the stream. And I'll show you that later. It's not really essential to the key point I'm making. All right, so let's go ahead and take a look at the time test method. This just goes ahead and times how long it takes to run. Here's the actual run test method that does the actual work. So this is where all the fun stuff really happens. As you can see, it takes a prime checker function, which is either a memoizer or the is prime method directly. And we print some diagnostics saying that we're starting up. You can see that when we run this thing, it says starting test with memoizer with count equal 20. It's just showing you what gets printed. We reset our atomic integer counters back to 0. And then we go ahead and create a publisher. And the publisher is going to be used to emit a bunch of data, emit these random integers. And as we'll see, this is either going to use backpressure or not. We can control that. And that's going to give us back a flux integer, which we call publisher. Notice that nothing has actually started at this point. This is a lazy evaluation, just like with streams, and nothing happens until we actually subscribe. We're then going to do some really cool stuff. This is some fun things I've been having kind of from a debugging and visualizing point of view with Project Reactor. So what we can do is we can go ahead and essentially take the publisher and we can transform it such that if we've enabled logging, then we'll log at the output. Otherwise, we just ignore it. And here's what log if looks like. If logging is enabled, then log if turns into flux log. Otherwise, it just turns into the flux. Or it doesn't turn into anything. It just comes back as the flux that came in. So this is the transform method. Transform is a way of being able to essentially mutate or modify the flux stream at instantiation time. So this will do the transformation when we make this call. So whatever logging enable is set to, that's what's going to make the decision. There's also something else called transform deferred, which does that decision at subscribe time. So this works at instantiation time, in other words, right here. Whereas if we use transform deferred, we could have turned logging on later, and as long as it occurred before we subscribed, then we would get the logging. I just need to use transform in this case because I'm going to turn logging on or not. I'm not going to defer my logging. Then we're going to go ahead and set PublishOn. And you'll see, actually, let me go show you Publisher first before I keep going in my little stream here. So here's the Publisher. This is the element that's going to emit the data. And this is really cool. So we're going to pass in a scheduler, which will be the Publisher scheduler, which might be different from the subscriber scheduler or not, depending on how the options are set. We're going to go ahead and get ourselves an iterator to all the random integers. So if we have 100 random integers, we now have an iterator to the random integer, to the random integers. And then we're going to go ahead and use flux create. And if we come over here, you can see that flux create is going to create a flux of integers. So we're going to create a flux stream of random integers. And here's what we're going to do. We're going to use this interesting thing called a flux sink. And a flux sink is basically what can be used in a hybrid push-pull model to let downstream subscribers request the next chunks of data, which would then be generated by the callback on request. So let's kind of take a look at this. Now, the first thing we're going to do is there's a hook method called on request, which that's what's actually going to be called by the framework under the hood by the downstream subscriber whenever we request more data. And so in this case, when we're requested to send more data, it's going to come in as the size, and we're going to print the size so we can see what it is. And you'll see that there's different ways of doing the size. One way is if you have an unbounded stream, you give a gigantic number like long max value or integer max value, which basically says just keep going pretty much forever. There's no back pressure at all. And we can toggle this, as you'll see. What we do then, let's assume for sake of argument that we have some reasonable size here. What we're going to do at this point is we're going to try to publish size number of elements. So size number of items. And what we do is we go into a for loop for I equals 0, I less than size. And as long as the iterator still has something left to send, and the iterator here is basically serving as a proxy from some input device. As long as we have input to send, we get the next element from the iterator. We print some debugging information that will be helpful when we see how flow control is needed. And then we go ahead and tell the Flux sync, here's the next item. You can now send that through the stream to be processed up to the subscriber. You'll notice here that as long as we haven't hit the end of the data in the iterator, whenever we're done with our loop, we return waiting for the next time we're called back by the subscriber up the stream. When we finally reach the end of our iterator, however, we are done, at least for this particular example. And then we say, hey, sync, we're complete. And that will then shut things down. So that's how you go ahead and send the complete event. You emit or signal the complete event up the stream is when you're done with the input. Now, obviously, there's some types of input where you're never done if you're reading a sensor, for example. But for this particular example, I wanted to bound it. But even with a bounded size, you'll still be able to see the flow control issues here in a minute. So that's what this on request thing does. It generates a bunch of events. And the last thing on the way out of this Flux create method is right after that's finished, we subscribe on the scheduler, which basically is the publisher scheduler. So that means that all the things I just showed you, all this computation here is going to be done in the context of the publisher thread, which comes out of that particular scheduler. So keep that in the back of your mind when we look at the next piece of the puzzle here. So let us now go back up here to our Flux stream. So we've got a publisher, and we've started publishing the data. It's going to be logged or not. And now we're going to put a PublishOn method. PublishOn is basically like observeOn in RxJava. And what PublishOn says is, for everything that comes after this, run that in the particular schedule that we provide as an argument. Oh, and here's the initial request size to use to start things going. So you can think of this as basically how much to fetch from the input stream. It's kind of the initial call to that on request callback with the size field there. So PublishOn, I think PublishOn by default will give a size of 256. I wanted to be able to restrict that. So I have this method called next request size we'll look at in a second. So PublishOn basically says use this subscriber scheduler thread for all the consuming, for all the subscribing, and that then applies to everything from that point downwards. So this map call and this subscribe call can then potentially run in a different thread of control altogether, or not, depending on how we've configured the test. For the starting point, just for fun, I'm going to have the publisher and the subscriber run in different threads, just so you can get a feeling for this issue of growing without bound if you're not careful. So what do we do? We're going to use map. Map's going to take each random number, and it's going to check to see if it's prime, and it's going to check that by using the prime checker, which is either the isPrime method or it's the memoizer. This code doesn't really care. So that's a good example of the nice use of like the strategy pattern in a sense. And then the final thing we're going to put in here is the subscribe, where we're going to give it mSubscriber. And mSubscriber is the hybrid push-pull back pressure model of flow control in RX Java or in Project Reactor. So that's basically the flow of what we're doing. Now you'll also notice something else interesting. Just for testing purposes, I built a little countdown latch into my subscriber implementation so I can wait for it to be done. And I'll show you that when we look at the subscriber in more detail. After we're done, we're going to go ahead and print the outgoing information. If you go back over here to run, you can see when we're finished, we say something like leaving test with Memoizer with 13 prime checks and 7 duplicates. So for the Memoizer version, we keep track of the duplicates. Obviously, for the one that doesn't use a Memoizer, there's no checking if they're duplicates. There might be, but we don't know. So then we just say there's 20 prime checks. And here's the clever way we do this. We're going to come in here. We're going to print out what M prime check counter has been keeping track of in terms of the number of prime checks. And then we're going to say, is our prime checker a Memoizer? In which case, we're then going to compute the number of duplicates. Otherwise, we don't compute the number of duplicates because we were using the non-Memoizer version, which doesn't keep track of whether they're duplicates because it doesn't use memoization. That's just a clever little way to get these statistics that make it interesting to see what happened. All right, so that's the overall flow. So I showed you what the publisher does. It's going to emit these streams of random numbers up to whatever the size is that's requested. And you can see that there's this method called next request size. It kind of starts things off. Let's go take a good look at the subscriber now and see what it's doing and how it's going to be working with hybrid push-pull backpressure. So here's the class hybrid backpressure subscriber, which is a subscriber, and it's also a disposable, so we can dispose of it later. We keep track of the pending items. We keep track of something called the subscription. That's very important with respect to backpressure and the way we're using Project Reactor, reactive streams. We keep track of whether we've been disposed or not. Here's our countdown latch that's used to control when we're finished for testing purposes. And here is the request size. So when we turn on the flow control mechanisms here, we're going to be requesting a number of items in terms of blocks of request size chunks. And you'll see that this isn't exactly honored by this Project Reactor implementation, but it's pretty close. We also keep track of the number of items that we processed since the last request. And this is basically the way that the subscriber knows when it's done with all its processing, so it can turn around and ask the publisher to send it the next batch. And you'll see sometimes this gets used, sometimes it doesn't, depending on the options we're using. Here's the constructor. We pass in the pending item count, atomic integer, and stash it away. We set M is diagnosed to false, and we start out with M items processed since last request to 0, because there hasn't been anything processed at the beginning. Let's now take a look at a bunch of hook methods. These are the hook methods that are defined by the subscriber interface. And interestingly enough, if you want to take control over backpressure in this fine-grained way that I'm doing here, you have to implement, or you have to basically implement the subscriber interface. You can't use the various lambda-based subscribe methods that come out of the box. They don't give you enough control. So you have to do something like this. And that's kind of a shame, but that's the way it works. So the first thing is called onSubscribe. This is the method that's called back by the framework when subscribe is hit. So this is a hook method that says, subscribe has just occurred. You want to do something at the beginning? And the answer is, yes, we do. We want to create a countdown latch with a value of 1 so that we can wait for the processing to be finished. We want to stash away the subscription that's passed in as a parameter for later use. And this subscription is going to be used in order to request chunks of data. And then the last thing we do in onSubscribe is we set our initial request here, which is going to be next request size. And we'll see what that does in a second. So that's another way we kind of kick things off. And you'll see why we need to do that in some cases. And this will make things more clear because we're not always going to be doing the call to subscribe on the, we might not always be subscribing on the publisher being separate. So we have to make sure that we always initiate the request. Here's next request size. What we do is if backpressure is not enabled, then we say send it all, or send it all in one fell swoop. And of course, that's rather problematic, as you can imagine, because if you send it all in one fell swoop and the publisher is running a lot faster than the subscriber, you're going to eventually end up consuming all of the memory resources in your program, and that will lead to an out-of-memory error, which is bad. But just for demonstration purposes, we're going to use the disable backpressure flag here, and you'll see how that affects the outcome. If we're not disabling backpressure, then we're going to request basically 10 items at a time. And we can make that whatever we want. I just picked 10 as a starting point. Here's the hook method. This is called onNext. This gets called back automatically when the next item arrives at the subscriber. And I've commented out some of the debugging stuff that indicates whether the results were prime numbers or not, just to get at the essence of the results that we care about. There's this thing called pending item count. Every time we consume an item, we decrement the count. And every time the publisher publishes the item, it increments the count. So this keeps track of the number of integers or items that are in flight, if you will. And obviously, as that number grows and grows and grows, it indicates that queuing is using up memory to hold all those intermediate values between the publisher and the subscriber. So obviously, if this grows without bound, you're eventually going to have problems. And we just use this to kind of show how the problem is either worsening or not, depending on what mechanism we're choosing. Then we come down here. We increment the number of items processed since the last request, and if it equals the request size, that means that we've used up everything in our window. We then go ahead and print a diagnostic saying we want the next tranche or the next chunk of these items. We go ahead and ask the Flux sync to send us the next chunk if we're doing this in the hybrid push-pull model, and then we reset our counter back to 0. And that'll keep going. Every time onNext is called, it'll increment, and we do the same thing. Here are just a couple other little helper methods. OnError is called if an exception occurs. OnComplete is called when we're done emitting the last item, and it bubbles up to the subscriber. And in addition to saying we're completed, we also release the countdown latch because we're all finished. And then we got a couple of methods that are used to either set the isDisposed flag to true or indicate if we've been disposed. And then finally, we have the await method, and this is what the calling thread uses to wait for all the subscriptions to finish in the producer-consumer threads that are doing the publishing and the subscribe. And again, this is mostly here just for testing purposes, so I could show very specifically what's going on. So that's the subscriber. Now let's go ahead and take a quick look back over here at the checkIfPrime method. That's another one that we're going to use to do some work. So checkIfPrime, you can see it's going to go ahead and make a new result object, which is going to have the prime candidate along with whatever happened when we applied the prime checker. And remember, this prime checker comes in as a function, but it's either the isPrime function, which we're about to look at, or it's the memoizer. So it might be just looking the value up in the hash map and returning whether it's a prime or not, or it could actually have to go to the trouble of computing it every time, or only if it's not a duplicate. Here's the isPrime method. We instrument this by this prime check counter, which increments by 1 every time we check to see if something's prime. That lets us know how many things were duplicates. And this is just the incredibly inefficient prime number computation algorithm intended to do nothing but burn CPU time to make the subscriber thread run much slower than the producer thread or the publisher thread is capable of running at. Okay, so armed with that knowledge, now let's start to play around with this stuff, and we'll turn on debugging, and you'll get a chance to see what happens if you turn off backpressure. So if we disable backpressure, if we make backpressure false, meaning send it all in one fell swoop, and we send a very large number of items, let's have some fun. This is really going to slow things down. I'm going to send out 2,000 giant prime numbers. I'm obviously not going to run this thing for very long because it's going to chew up all my memory. And I'm also going to go ahead and turn on debugging and watch what's going to happen when we run this program. So when we run this program, you're going to see that it's going to send all the items in one fell swoop. So it's going ahead and sending all of these different items here. And these items are all out basically pending. And you can see it's all on the publisher's side of the house. So the publisher is the thing that's doing all of the processing of this stuff. And I don't even know if oh, here we go. So after all of the publishing has finished, right, when we're finally done with publishing, then the subscribers get a chance to run. So I think you'll agree this particular program is saved by the fact that I limited myself to 2,000 of these guys. But in reality, if this was an infinite stream of data, the numbers keep growing and growing and growing. And of course, these poor subscribers are going to have a hard time keeping up. So let's go over here just to make sure I'm running this right. Oh, okay. So for this particular example, we have disabled the back pressure, and so it'll just basically send all the items, and it'll do them all in one fell swoop. And that's really not what you want, because you can see here it's taking us quite a long time to burn down all the things that we sent here. Every time it's requesting the next tranche of items, that is being ignored because we've already sent all the items. So it's not doing anything. So this is not the way to do things. I think you can see that we're using a ton of resources. So let's go back here. I'm going to stop this running because it's going to go on forever. And let's turn the back pressure to true. Now, this will also take a long time to run, but we're not going to see the number of pending items grow without bound the way that we saw before. And so what's going to happen is it's going to start out by generating 10 items. And you can see that the number of pending items is basically pegged at around 10. And then the subscriber is going to do some processing. And then it's going to request the next tranche of items. And then the publisher will publish stuff. And now we've got much more of what you'd expect to see here. Publishers and subscribers are both running concurrently. In steady state, they're kind of running in parallel. Whenever we reach a point where the subscriber doesn't have anything else to do, it goes ahead and asks the publisher to send the next chunk of data. And we could probably fiddle around with when we actually make that request, because we probably want to make the request a little bit early so that we keep things going. And in fact, if you take a look, you can see that that's exactly what the framework is doing on our behalf. I'm asking for 10 items, but I'm getting 8. And that way I've still got stuff to process before the next request comes out. So I think you can see here that there's much better interleaving now between publishing and subscribing. And also if you take a look, hold on a second. Let me get rid of logging. Let's see, let's turn logging to false. Logging is a useful thing to have, but it also can distract you. So let's have a little bit less stuff flying around on the screen, and I can explain it better. So here we're starting over again. You can see that there's this nice interleaving between publishing and subscribing, and that's what we want to have. That way we're not having a large queue of data that is going to keep growing and growing and growing. We never have any more than basically 8 to 9 items in flight at a given time. And you can also see this nice interleaving of subscribers and publishers. And that's another reason why I've got these 2 different pools here, so you can see who's publishing and who's subscribing, and they kind of go back and forth, and they run pretty much in parallel. Okay, let's try something else just for kicks. Let me ratchet down on the number of items we're going to emit, because that's an awful lot. And let's turn parallelism off. So now we're going to run everything in a single thread of control. So as you can see here, we're going to run this. Now we're running this with only a single thread. And it all works again. At least I hope it works again. And you can see here that we have the thing going through and doing the requests and so on. It worked, which is good. Depending on how what you're doing, it may or may not take longer to run. It obviously depends on the computations you're doing. But you can see here that we can have everything running in one thread, which is what we have here. So everything's running in the subscriber thread. I could conversely have had everything running in the publisher thread for that matter. But you can see now that it's much more, everything is sent from the publisher. Everything is processed by the subscriber. Then it makes the next request. A bunch more stuff is sent by the publisher. then the subscriber handles it. So there's very little or no interleaving taking place in the single-threaded model, which is, of course, what you'd expect. There's only one thread. And that's the benefit of running things with the, that's the benefit of running with it concurrently, is we can overleave the reading of the data and the processing of the data. But be aware that for something like this, even with memoization, computing prime numbers takes time. And so the publisher can produce data a lot faster than the subscriber can consume it. Okay, couple more things I want to show you. Actually, I want to show you something else that's kind of interesting, because it's important to understand the pros and cons of memoization. So let's go ahead and disable debugging. And let's make us have, I don't know, 2,000 elements, but have much smaller numbers. Let's see if we can get the behavior I want. So let's say that we do this. This shouldn't take very long to run. So we have 2,000 items, and you can see that the memoizer is actually, the non-memoizer version is actually better in this particular case than the memoizer version. And you can see that there were a lot of duplicates, but because the processing time is much lower, it's able to do because each of the numbers is very small, checking the numbers to see if they're prime takes very little time. So it's actually faster when you have small values to compute whether they're prime or not, rather than caching them. So there is obviously a cost of caching. And obviously caching is a bigger win the more time it takes to figure out whether an item is already been, or figure out the computation. So in other words, for long-running computations, the cost of caching is worth it, because you're going to get the results back very fast, and the overhead of caching is minimized. So it's just kind of showing you that caching is not a panacea. There's a cost to be paid by that. Last thing I'm going to do, and then I'll take some questions. I want to go down and take a look at the part of the code that will demonstrate slicing. And this is just illustrating how you can do slicing with the reactive streams model. So as before, we take our map, we sort our map, and then we print the primes followed by the non-primes. So here's how we are going to go ahead and sort the map using RX Java features, Project Reactor features. This is almost identical to the way you do it with regular streams. The only difference is we don't do a stream factor method. We use from iterable. So we take the entry set of the map, we make it into a flux by using the from iterable factor method. We sort with the comparator. That's pretty much identical to what we had before with Java streams, and also identical to what we had before. We use collect. So that's the cool thing about Project Reactor. You can use collect, use exactly the same collector as we did for our streams-based version. And then in this case, we just block until we're done. So we get back a sorted map. Then what we're going to do is we're going to go ahead and pass that into print primes. What this will do is it will go ahead and again, now take our sorted map, turn it into a flux of map entries. And then we're going to take the entries from this stream, the flux stream, as long as their values are 0, meaning they're prime numbers. Then we go ahead and switch back to a flux of integers based on the keys. We collect that to a list and we block. So I think you can see, again, it's pretty much identical to the way you would do it with streams. Same thing for the print non-primes method. Once again, we convert our entry set into a flux, which is a stream of integers in this case. And then we use skip while. And skip while is basically the Java streams version of drop while. Java streams also has a take while method. So take while is the same in both. For some strange reason, the folks with RX Java and then Project Reactor decided to call it skip while, not drop while, but it's the same idea. So we're just going to skip over everything that's prime and then give a flux stream of non-primes, which we collect into a list. So anyway, I just kind of wanted to show you that. Very much the same kind of code. So this is a very interesting example. I will continue in future sessions to explore other dimensions of backpressure with reactive streams Project Reactor, most likely, because the RxJava stuff is about the same if you use flowables. And we'll learn about other things, because you can also take other control over the strategy of what happens when your buffers get too big, the queues that are being used to buffer items. And you can do things like decide to drop stuff. This particular hybrid model avoids this problem by not trying to have a giant buffer, but instead it gets things in chunks. There are other models where you can have giant buffers, and then you can decide to only keep the last item or only keep the last n items, or buffer forever until you run out of memory, and so on. So we'll take a look at those strategies later. So with that in mind, let me go ahead and stop the video, and we will take some questions. Let's see. There we go. Let's see here. So if the publisher and the subscriber run in the same thread, there's no need for backpressure. No need, but yes and no. I mean, you're still going to have these buffers that are used. And so I think you're still wise to do it in that particular case. It's just that the buffers aren't between threads, but the data, as you saw when we ran it in a single threaded model, it would still have to buffer all those items before the consumer would get a chance to run. Sync next always gets called in one thread. In this particular example, it's getting called in the producer thread. I'd have to play around with it more to see if there's other scenarios where you can have it called in multiple threads. I think probably best to keep it in one thread. I think that's one of the rules with reactive streams. Subscribe keeps track of the batch side passed through PublishOn. So as we saw, the way that subscribe worked was that PublishOn was used because we had a separate thread for the producer than for the publisher rather than the subscriber. So we used PublishOn, this is a strange thing, but we used PublishOn to give the subscriber a separate thread, and we used SubscribeOn to give the publisher its separate thread. I've always thought that that was a bit backwards, but I'm sure there's a good reason for the names that they have. But basically we used, subscribe was able to use the subscriptions request method in order to request stuff. So that's another way you can, there's several different ways to get these requests to percolate upstream to the Flux sync. When data is requested in batches, does the pipeline run when the entire batch of data arrives? Well, I think as you saw when we interleaved it in multiple threads, it was still able to be doing other processing, and it would again get the next chunk sent up to it. And that's basically what the concept of prefetching is all about. You want to try to keep the pipeline busy on both ends. And I probably have to improve my implementation a bit to get it to work more effectively in that respect. But the idea there is you want to be having the subscriber probably not wait till it's run out of items before it makes the next request. Because if you can balance it a little bit better, then you're going to keep the publisher and the subscriber working in parallel, which is kind of the point of doing this producer consumer model. So there's probably some fiddling around I need to do with when I do the requests, but I haven't had a chance to play with that yet. When we say the subscriber starts processing, do we mean the entire pipeline or only the consumer action that's passed to subscribe? So when you subscribe a subscriber, when a subscriber is subscribed by subscribe, a little redundant, that's what sets everything in motion. So streams, if you think about Java streams, the normal parallel sequential streams, none of the intermediate operations or the data source does anything until a terminal operation is called. And the same basic idea, so what we say in that case is streams are lazy. And the same basic lazy model applies with reactive streams. So nothing is being published, nothing is being mapped, and so on, until a subscriber subscribes. And you saw those various hook methods like on subscribe and so on that are called just before everything starts to run. So the way to look at it, and the way I look at it, is with reactive streams, when you subscribe, that's a signal that tells the publisher to start emitting the data. So it's then pushed through the stream to the subscriber. With Java streams, when you have a terminal operation, that starts things pulling through the stream. So that's kind of the difference. The streams model is really entirely pull-based. The Java Streams model is entirely pull-based, whereas the RX Java or Project Reactor model is more of a hybrid. In fact, we saw that hybrid nature there, right, with the Backpressure. So we start things running, and we start by having the Flux sync, in this case, push a bunch of data to us, which is either an infinite amount of data or it's a chunk of data. And so with a hybrid model, you can kind of have, pull-based pushes. So you can say, pull me 10 items, and then those things are pushed to you. And then you're like, okay, thank you. Pull me the next 10 items or the next n items and so on. And the framework tries to be clever about how it actually does those things. Let's see. Can you explain the purpose of the schedule that's passed to PublishOn? The schedule that's passed to PublishOn is what enables the subscriber to run in its own thread. So if we don't have that call, or if we don't give a different scheduler, everything runs in the thread of the publisher. So if we don't do that, then we don't have a producer-consumer concurrency model. We just have a single thread of control running asynchronously. Is sync similar to consumer object be created in Java? Excuse me. Is the sync similar to a consumer object being created in Java Streams for each intermediate operation? Yes, you can think of it something like that. In fact, it is a consumer. Can we use multi-subscriber to handle the data from one publisher if the data arrive is huge? Yeah, so we're in upcoming webinars, we're going to take a look at other aspects of using these features with Project Reactor and Reactive Streams. So this particular example was just meant as a starting point where we're going to end up having a publisher and a subscriber. But we're going to look later about how you could have multiple subscribers in order to be able to kind of offload the work from one thread. And as you can see, I'm not even really sure if having multiple threads is a big win here in the way we've done it. But if we can have multiple subscribers doing that in parallel up to the number of cores, then I think we really will start to see a big boost in performance. That's also, of course, if you don't have that feature, then parallel streams are going to be a much bigger win because they're going to be able to basically kind of shard the input data and run in different cores. So we'll be exploring those dimensions in later discussions. And I think if you've seen some of my other tutorials, we've talked about ways of doing things in parallel and so on by using things like parallel fluxes or the famous flat map idiom to get things to run in pools of threads. So we'll be looking at that in upcoming sessions. All right. Well, these were great questions as always. Hopefully you guys enjoyed this first look at Backpressure. There's a lot more to the subject that I will cover in upcoming sessions. I have found when I look on the web, it's actually surprisingly difficult to get much coverage in a concrete way of how to do Backpressure, especially with the advanced features. It's very, very hard to find tutorials, especially on Project Reactor. You can find a bunch of stuff on RX Java, and I guess the Reactor folks are like, well, we're basically RX Java, so we don't have to have our own tutorials. But I will try to fill in some of those gaps because I had to do a lot of playing around, just experimenting with different things to see what I could get to work. So hopefully this will be useful to people who are trying to do something similar and are still a bit mystified by how all the different features work. But we'll continue to expand and improve this. One of the things I think we might do in our upcoming session, I'll keep playing around with the Backpressure stuff, but it may take me a few more days to get all the examples working the way I want. What we may do in our next session is go look at ways of improving upon the memoizers we've been using. So the memoizer we've used thus far is an infinitely caching memoizer. So if you have long running streams of input and they range in terms of the values, you'll end up keeping cached values around forever, even if nobody is actually trying to use those values anymore. Imagine if the values were something like timestamps or dates or something. And after a while, you'd want to get rid of the old stuff out of the cache because no one was ever going to ask for that anymore. So we're going to look at some really cool examples of timed memoizers that will showcase some very sophisticated features in Java. In particular, it's scheduled executor service, as well as some other really cool examples of fine-grained synchronization, things like advanced features on atomic integers and so on. So that may be what we do tomorrow, but I will try to get back to the backpressure stuff as soon as I can, because it's an absolutely fascinating topic. And I hope you enjoy it as much as I do. So thanks again to everybody for coming, and I will look forward to seeing you again soon.